Hey there students, welcome to the solutions video for the practice test. There's time codes down in the description if you'd like to jump to a particular question. Alright, question one is all about evaluating some expressions. So when we see this word evaluate, what it means is we have to find the value of whatever the expression is. So say for this first one here, 0.5 plus 1.2, we just have to figure out what 0.5 plus 1.2 is, which for this one would be 1.7. Next one, 3.46 plus 1.7. You can do a couple of things for this. If you're a bit stuck, you can set it up as a column addition like this. Or, given that you're able to use calculators on the test, you can get your trusty calculator ready instead, which will give you the same answer of 5.16. If you wanted to try it like this first, and then check it with your calculator, that's fine. Or you can jump straight to the calculator, whatever suits you best. Similarly, this would be a 0.9, but you could check it with a calculator if you wanted to. Next one, 0.8 take 2.4 would be negative 1.6. Next one, 3.1 times 0.2. We times it by 0.1, that'd be 10%, so 0.31, and double that would be 0.62. But again, you could just double check it on your calculator to make sure you've got the same thing. And this last one, that's definitely possible without a calculator, but I think if you tried to do that, it's a bit fiddly and it's prone to error. So I'd be going straight to the calculator for this one. These are all worth 1 mark each, so it's a right or wrong situation. So best to get it right if you can. Okay, next one. A very important number in maths is pi, which is an irrational number. It starts off with 3.14159 and carries on forever without any repeating digits. Now we've got to round this number first to 6 decimal places, then to 3 decimal places, and then to 0 decimal places. So what we need to do in the first instance is look just up here. So 3.14159. So we want the first 6 digits. So 3.14159. Now for this last one here, this 2, we've got to decide whether to leave that as a 2, so round it down to a 2, or if we want to bump it up to a 3. And to do that, we look at the next digit, and if it's 5 or greater, we round up. If it's between 4 and 0, then we round down. So for this one here, that next number is 6. So we want to take this 2 and round it up to a 3. And the reason that we do that is because we're going to 6 decimal places, 3.14159 to 6 is closer to 23 than what it is to to 3 than what it is to the 2 below it. So that's why we round down for that one. Similarly, going to 3 decimal places. So where we have a look at these first 3 here, we've got 3.141. And now we look at the digit after that 1. If it's 5 or greater, we round up, which it is. So we're going to go 3.142 in this instance. And for the last one, we want to round it to 0 decimal places. So for this one, we start off with, well, we consider the 3, but then we look at the number after 3. So it's a case of, do we round the 3 up to a 4 or do we round it down to be a 3? The digit after that is 1, so we're just going to leave that at 3. But we're not going to write 3.0 because technically 3.0 would be to 1 decimal place. So we just want 3 for that one. Okay, next question. We want to write the first 6 decimal places of the following decimals. Pretty big hint here is to be careful with your rounding exclamation mark. The reason for that is, if we look at this first one here, we've got 0.6 and we've got a bar above the 6, and that tells us that the 6 is a repeating digit. So if we were to if we were to write 0.6 recurring as a decimal, we're going to get 0.6666666 going on for as long as we are able to, but we just want the first 6 decimal places for this one. So we want 0.666, so that's 3, 4, 5. Now, this is where you've got to be careful with rounding. The next digit, we've got to decide if we want to leave it as a 6 or bump it up to a 7. The next digit is a 6, which is 5 or greater. So we're going to round that up to 0.666667 for that one. Okay, this next one just here, the bar above the 592 means it's the 592 that repeats as a pattern. So it'd be 7.592, 592, 592, again, going on for as long as we could possibly do it. That'll go on forever. So when we're rounding to 6 decimal places, we want 7.592. So that's 3 digits, 5, 4 digits, 9, 5 digits. Then we've got to decide whether to leave this 2 as a 2 or round it up to a 3. The next digit is 5, which is 5 or greater. So we're going to round that up to a 3. For the next one, you're not expected to know what that fraction is off the top of your head. But if you do 547 divided by 999 on your calculator, you get this one. So 0.547547 repeating. So we'll do the same sort of thing that we did last time. So we'll start off with 0.547 and then 5, 4. And then we think, well, the next digit's going to be 7. Do we leave it as a 7 or round it up to 8? But then we think, well, the next digit is going to be a 5, so we do need to round that up to an 8. Now, similarly, 8 divided by 99 gives us 0.08080808. So I'll start that here again, 0.08080. And then, is the 8 going to stay as an 8, or is it going to be bumped up to a 9? The digit after it would be a 0, which is less than 5, so we're going to leave that as an 8. Yeah, similar situation for this one. It's 1 mark each, right or wrong. Okay, we just spoke slightly a little bit about recurring decimals or repeating decimals. So we've got to decide for these ones whether the decimal is a recurring one, i.e. is it going to go on forever, or is it going to terminate, which just means it finishes. And if we look at this first example here, so 12.345, it's 12.345 and there's nothing indicating that the 345 repeats in any way. So even though we've got decimals here, the decimals are not going to repeat. We've just got 12.345 and that's it. So this one is a terminating decimal. The next one, 5.9, well, if you're not sure, just do it on your calculator. 5 divided by 9 is 0.5 recurring, so we're going to say that that's a recurring decimal. For this next one here, negative 4.345, and then we've got this bar above the 9, which tells us that the 9 is going to repeat. So we'll put that in as a recurring decimal. And then for the next one, 50 and 2/5 as a percentage. That is pretty much just the same as 50.4%, because 2 divided by 5 is 4. Yes, it's a decimal, but the decimal doesn't repeat. It finishes there, it terminates. So we're going to call that one a terminating decimal as well. Right, now we're on to question 5, which is index laws. Okay, for this first question, you might have seen this written a little bit like this. So we'll talk about it verbally first. So 6 to the power 9 is 6 times 6 times 6 times 6, 9 times, right? And then 6 to the power 12 is 6 times 6 times 6 times 6, etc., 12 times. So if we multiply 6 multiplied by itself 9 times and then multiply it by itself another 12 times, what we're going to get is 6 to the power of 9 plus 12, which is 21. And notice as well that unlike the question before where it said evaluate, this one says simplify. So we don't need to find out what 6 to the power 21 actually, what the value of that is. We're just simplifying the powers. So that answer is done. Sometimes the way we show this is if you've got any base, in this case it was 6 raised to a power, and you multiply it by the same base raised to another power, you can simplify those by adding them together. Right, for the next one, when we divide, we multiply. And I'll just do a straightforward example just up here. If we had 3 to the power 5 divided by 3 to the power 2, 3 to the power 5 is 3 times 3 times 3 times 3 times 3, so 5 times. And then 3 to the power 2 is 3 times 3, like that. Now, I could cancel these off. 3 divided by 3 is 1, so that cancels off. 3 divided by 3 is 1, that cancels off 2. Leaves me with 3 to the power 3. But instead of writing it in expanded form and cancelling it every time, what I do instead is say, well, if I've got 3 to the power 5, I'm cancelling off 2 of those on the bottom. I'm going to have 3 to the power of 5 take away 2, which is 3 for this one. So similarly, for the question that we are working on, I'll just have a quick eraser party just at the top here. So we've got negative 3 to the power 30 and divided by negative 3 to the power 12. Don't let the negative 3 bother you, it's just what our base is for this question. So we're going to have negative 3 and it's to the power 30 take away 12, which is 18. And you'll sometimes see that written like this to help you remember. If you're dividing the powers, or dividing the bases, you simplify the powers by subtracting. But that helps you can remember it how you like. Now the next one here, we've got g to the power 4 multiplied by, or raised to the power 3. So g to the power 4 raised to the power 3. That's kind of the same as saying g to the power 4 times g to the power 4 times g to the power 4, which using what we learned up here would give us g to the power 4 plus 4 plus 4, which is 12. But again, rather than writing that out, if it helps you to expand it like that, great, by all means do it. But what you could do instead is just do 4 times 3, because we've got 4, lots of 3 there, so g to the power 12. You can remember that like this. Anything raised to a power again, we can simplify those powers by multiplying. Okay, and the next one, we've got to do a bit of a combination one. Now remember, we can only simplify powers if the bases are identical. So for all the ones that we've done so far, the bases have been identical and there's only been one of them. But for this next one, we have to do 8 to the power 3 divided by 8 to the power 2 separately. So again, we do 3 take 2, which gives us 8 to the power 1, or just 8. And then 5 to the power 9 divided by 5 to the power 1, there's an invisible 1 there, don't forget, would be 5 to the power 8. Cool, that's that one done. Okay, this next one combines what we just learned with some integers out the front as well. So, or some coefficients rather. So we've got h to the power 2 multiplied by h to the power 3. That was simplified to give us h to the power 5, because let's add those together. But then I've also got to do negative 2 multiplied by 4, which would give me negative 8. Because don't forget, for a question like this, in algebra, 4h squared really just means 4 times h to the power 2. We're timesing that by negative 2, and we're timesing that by h to the power 3 in this case. So for this one, we can do the 4 times negative 2 separately, which is negative 8, and the h squared times h cubed separately, which is h to the power 5. Okay, next one. We've got to raise everything in this bracket to the power 3, so we're going to use that multiplying again. Here, we've got 3 to the power 1 times 3, which is 3, and then m to the power 2 times 3, which is m to the power 6. We're supposed to simplify the powers for these ones, but it's kind of convention as well to, you've got something that's readily evaluated, like 3 to the power 3, so 3 times 3 times 3, which would be 27. We usually just write that as 27. So 27m to the power 6. Next one, we'll do something similar, but we've got a little job to do first. So we'll start off with 7p to the power 4. Then I'm going to expand this bracket by applying that 4 through the whole thing. I've got to raise negative 2 to the power 4. And I've also got to raise p to the power 4 as well. All right, now it's probably handy to figure out what negative 2 to the power 4 actually is. So negative 2 times 2 is positive 4, times negative 2 again is negative 8, and times negative 2 again is positive 16. So we want positive 16 here. times p to the power 4. 7 times 16, I'm going to cheat a little bit for this one for some quick maths. Yeah, very good, 112. And p to the power 4 times p to the power 4 would be p to the power 8. And lastly, this one looks really complicated because there's a lot going on, but the little thing that actually makes it not too bad a question is this guy just here, that 0 there. So anything to the power 0 is equal to 1, and for that reason all of this is equal to 1. So answer is simply 1 for this one. The reason for that is if we had 3 to the power 3 divided by 3 to the power 3, to take those powers away, it would give me 3 to the power 0. But if I thought about that as a fraction, 3 over 3, so 3 to the power 3 divided by 3 to the power 3, I'm just dividing it by itself, and anything divided by itself is 1. So yeah, anything to the power 0 is 1. Wonderful. Okay, next one we're going to list all the prime numbers between 20 and 40. Ooh, okay, so let's go through one at a time. Not 20 divisible by 2, not 21 divisible by 3, not 22 divisible by 2. Actually, I probably won't do that for the whole thing, so 23 is fine. Not 24, not 25, not 26, not 27 divisible by 3, not 28. 29 would work, as would 31. Not 33. 37 is a prime number, but not 39 because 39 is divisible by 3 as well. It's kind of late at night, but I think that's it. Maybe I'll do a voiceover if I check that later and it's wrong. And this next one, what is a composite number, and give an example. So these numbers here, these are prime numbers. They can only be divided by themselves and 1. A composite number is pretty much all other integers apart from a couple of special ones like 1, for example. So a composite number is divisible by itself, 1, and at least one other number. And it says give an example. So 20 is divisible, I'm trying to write this quickly, sorry, by 1, 2, 4, 5. Really, once you've listed one other factor, the rest kind of are redundant, but we'll do that anyway for this one. Okay, all that gives us a bit of practice for factor pairs. Okay, factor pairs of 24. So 1 and 24 are both factor pairs. And the reason they're a factor pair is because 1 times 24 equals 24. But now we've got to do that for all other factors of 24. So now start with 1, I'll move up to the next number. 2 fits into 24. So 2 fits into 24 12 times. So 2 and 12 would be the next 2. 3 fits into 24. 3 fits into 24 8 times. I'll go up to 4. 4 fits into 24 6 times. So 4 and 6 are both factors. And can I go any further than that? 7 doesn't fit in there. 8 I've already covered, and then I'll be going back in the other direction. So that's gonna be all of them, I reckon. Okie dokie. What's next? All the factor pairs of 36. We'll do something similar for that. 1 and 36. 1 times 36 is 36. 2 times 18. So 2 and 18 gives us 36. 3 and 12 give us 36. 4 and 9. So what you'll notice I'm doing here, I'm starting with 1, I'm checking 2, I'm checking 3, I'm checking 4. So 4 and 9. 5 won't work. 6 will work. But I'm not writing 6. If it's factor pairs, maybe I'll write 6 and 6, because 6 times 6 is 36. So I guess technically it's a factor pair. But if you hit a square number that's a factor pair, we definitely don't need to go through like that. And then using our results from parts A and B, what's the highest common factor for 24 and 36? So we want to look for the largest number that fits into both numbers. And I reckon 12 is going to be our winner for this one. Okay, because 12 is the largest number. I've got a 12 here and a 12 here. It's the largest number that is common to both. Okay, first three multiples of 24. So multiples are pretty much just like the times tables of a number. I'm starting off with 24. That's 1 times 24. The next multiple is going to be 48, which is 2 times 24. The next one is going to be 72. I'm pretty sure. Just let my late night brain double check. Yeah, that's right. So we just wanted the first three for this one. For 36, we've got 36, which is 1 times 36. 72 is the next one. And then if I added 36 on again, I would get 108. Now, using our results for those two questions, what's the lowest common multiple for both of those numbers? So we're looking for the smallest number that 24 and 36 both fit into, which is 72. Okay, all right, so for everything we've done so far on this page, it's pretty much, I'd say 1 mark for each pair, maybe missing one, maybe 1 mark less for a mistake. Similar thing for these ones here, but the multiples are easier, so it's just 1 mark for the whole thing. The next question, though, is a massive one. It's worth 10 marks. So what we want to do is start off by using factor trees. We want to identify the highest common factor and lowest common multiple of 56 and 88. So I'm going to start off with my factor trees for this one. I've got 56. I'm going to divide that by, I like to divide by primes. You can divide by any number really. 56 divided by 2 would be 28. 28 divided by 2 is 14. 14 divided by 2 is 7. Okay, so now I can express 56 as a product of primes, which is 2 over 3. It's 2 to the power 3, that's for sure. 2 to the power 3. Oh, I made it go away. It's back. Cool. 2 to the power 3 multiplied by 7. Right, now I'll do my factor tree for 88. I'll divide by 2, why not? 2 times 44 is 88, divided by 2 again. 2 times 22 is 88, divided by 2 again. 2 times 11. And now I can't go any further because I've got all primes just there. And I can write 88 is made using the product of 2 to the power 3 and multiplying that by 11. Okay, this is where the next part is kind of tricky and is probably more like the extension end of what we've been doing in class recently. But what we want to do for the highest common factor, we want to consider what we've written as our product of primes for 56 and for 88 as well. What we want to do is take the power of, we'll have a look at the powers for each of our prime factors, and whatever's common to both of them, we want to take the highest power that's common to both and pretty much multiply it through. So if I look through both of my answers here, I've got 2 to the power 3 just here. I've got 2 to the power 3 here as well. So that is common to both. Now, 7 to the power 1 isn't common to both of them, so I'm not going to use that. 11 to the power 1 isn't common to both of them, so I'm not going to use that either. So my highest common factor for these two is going to be 2 to the power 3, which is equal to 8. Okay, so that's part 1. That means that the largest number that fits into both of them is 8, and that's a cool trick that you can use to do that. The next one, the lowest common multiple, we want to do something a little bit different. We want to pretty much involve every factor in some way this time. So I'm going to look at it's not the highest one that's common to both of them for this one. It's going to be straight up whatever the highest one is. But here we've got 2 to the power 3 and 2 to the power 3. So I'm going to use that 2 to the power 3. I've got a 7 involved here. So I'm going to multiply that by 7. And I've got an 11 involved here as well. So my lowest common multiple is going to be given by 2 cubed, which is 8 times 7 times 11, which gives me 616. Okay, so that's the smallest number that 56 and 88 both fit into. And rather than literally writing down 88, go through the 88 times table, you can find it using products of prime factors, which is a really, really neat trick to be able to do. I'll leave some links to what I'll do for all of these. Actually, I'll leave some links to extra practice in the description. If you're going for the very top marks, this is maybe one to consider giving a go. Okay, last question. Thanks for sticking with the video. So 2 slot cars, which is kind of like scale electrics, are racing around a track. One car completes a lap in 18 seconds and the other completes a lap in 16 seconds. If they cross the finish line at the same time, or the start-finish line at the same time, how many seconds will it take for the cars to cross the start-finish line together again? So essentially here, we've got a track. So one car is going to take 16 seconds to go all the way around, and the other car is going to take 18 seconds to go all the way around. So when the first car gets over the finish line, the second one is just a bit behind. Then on the next lap, the car that's a bit faster is going to take another 16 seconds. The first car is going to be starting a bit behind and is going to maybe make it around to here. So it's always going to be a couple of seconds behind. What you've got to figure out is how many seconds will it take until they're crossing that finish line at exactly the same time once again. So this is a lowest common multiple question. You want to find out the smallest number that 18 and 16 both fit into. And there's a couple of ways that you could do that. One would be to list the multiples of 16 and list the multiples of 18 and figure out which is the smallest number that comes up first. So multiples of 16 would go 16, we'd go 32, we'd then go 48 and so on. 18 would start with 18, then we'd go to 36 and so on from there. But what I might do is take this as an opportunity to re-demonstrate the technique we had a moment ago. So 16, if I express that as a product of its prime factors, I happen to just know that off the top of my head. It's, hang on a sec. So we've got 2 to the 2 multiplied by 8 gives us 16. 8 is 2 times 4, and 4 is 2 times 2. So 16 is the same as 2 to the power 4. That's a common one that you might just remember. You might not though, that's okay. Whereas 18 we could do as 2 times 9, and 9 we can do as 3 times 3. So if we do that as a product of its primes, 18 is 2 multiplied by 3 to the power 2. Now, using what we did a moment ago, what we can do instead is say the lowest common multiple is going to be equal to looking for the highest power of 2, which is 2 to the power 4, and the highest power of 3, which is 3 to the power 2. So I'm essentially doing 16 times 9 for this one, which is going to be 144. Generally speaking, if you're given a worded question, it's nice to give a worded answer. So if our question now is how many seconds will it take for the car to cross the start finish line at the same time again, we can say therefore the cars will take 144 seconds to cross the start finish line together. And again, for this question, using that technique for lowest common multiple with the primes was optional, but I think that if you know how to do it, you can do it a lot faster. So I think it is worth giving a bit of time to. Okay, thanks for your attention. Good luck for your test. Goodbye.